let's talk about bloat, database bloat. To be specific, even Postgres database bloat. And I really enjoy talking about this because this topic is so deep into the fundamentals of how things really and truly work on database systems. You see, when databases work by the concept of pages, pretty much everything is a page in databases. When you want to read something, right, a database store, when you read, let's say, a single row or an index entry, you don't get to read just that row. That row or that index entry lives in a fixed size page. And MySQL AnnoDB, it's 16 kilobytes, and MongoDB clustered collections, that's 32 kilobytes, and Postgres, it's 8 kilobytes. It's a fixed size, and it has a header, so there's like a little bit of a overhead to the page itself, but we need metadata to store the page itself, right? And then in the page itself, there is a data portion, and in that portion, we store the rows, right? Another question becomes, how many rows can I store in a page? It's a fantastic question. If you can really truly answer that question, you really understand what you're doing, especially in the data modeling aspect. Very few DBAs actually think that way. It's really sad, because that's the fundamental basic principles. Like, how many rows can I get in a page? It's a very difficult question to answer, to be honest, because it depends on your storage type. Are you using column versus row store? And we mainly play with row store, so let's say it's row store. Then, the data types. Are you using native data types? Or are you using like text? And based on that, the rows, the columns will be either stored in line. When I say in line, I mean row, the first row will be literally stored here, the first column, second column, third column, fourth column, fifth column, and so on, right? And then the second row starts right after that. And then first column of the second row, second column, third column, right? So naturally, the more columns you have, the less rows you can store. But that's not our topic. We can dive deep into that at any point of time. But it's fantastic to think about this. I absolutely love it. Back to bloat. The page, when you first create it, it is, can we agree that if I do an I/O to fetch a page, from disk, which is 8 kilobytes, let's say, right? Regardless of the definition of an I/O, whether it's single or multiple, because that's also another complex question to answer, because it depends on the file system, it depends on the SSD page size there, the block size, and in the file system block size, and based on that, whether you have cached or not. But let's say we get one I/O to fetch one page. That's the cost. It's a 1 unit to fetch one page. Okay? And we might be lucky and we have that page stored in the shared buffer so that our I/O goes into the shared memory instead of actually going to disk and copy it into the file system cache, and then from file system cache we copy it again to the shared memories. That's also another cost, right? But there is a cost to obtaining that page. It's a 1 unit IO. And if you get that page and you look at it, the goal is to have as many rows that you want as possible in that IO, right? Because it's really kind of sad to fetch a page only to see that all of the rows are deleted in that page, right? Or it's mostly empty space. That's just the worst case scenario. Because when you do an IO, you're looking for something. And either if it's a point query or a range query, you try to look for something. You're trying to find it. And if that page is filled with empty space, then you need to do another IO to really look for the stuff that you really want, right? So we agree that it's, in Arabic we call mustahab. It's mustahab. It's really advisable to have as many rows in this beautiful page, packed, right? So that a single IO gives you a lot of rows. And not only that, it's even better if all the rows that you actually want are in this page. That's where indexing comes from into the picture. Fascinating. All right, now let's come to Bloat. You have an empty table. You started inserting a lot of rows. Right? You filled it up. Let's say you have 10 pages, 20, 30, 100 pages of rows in this, right? And then each page will have X number of rows, right? And it doesn't have to be the same number of rows, no, because some rows are thin, some rows are fat, because some of the rows will have populated columns, some of them will not. So databases are smart. They will not fill up the columns with stuff just because you don't have it, right? So you will have one page that have 10 rows, one page that have 100 rows, right? Some pages will have just a very big rows that will take only 5 rows, right? But then you have this. Now you started updating and deleting. You're doing all sorts of things. When you delete a row in Postgres particular, or update one, when you update, a new version is created. So just by doing that, the old tuple is marked as deleted. It's marked as gone. That's it. It is instantly available to be reused. Well, that's a wrong statement, instantly, because the deleted row, the old version, the old tuple might still be needed by older transactions. So it's not clearly ready to be used yet. Vacuum actually does that and decides that based on the horizon of the last X-Men. Says, all right, I can clean up this because nobody's using this row anymore from all the running transactions. So we wipe it out and clean it up. But regardless, as you delete and update and you delete and update, you will have clean places, gaps, fragments in those pages with nice spaces to be used, which is fantastic, right? It's actually fantastic. Why? Because new written rows will use these empty spaces, right? Because if I insert a row, I don't have to go to the last page, right? I can definitely reuse one of these empty spaces that I've just vacuumed and cleaned up. I can insert stuff in there, right? So you can start doing that. So that's the fantastic part. The ugly part is if you do that a lot, then, and you don't insert as much, what will happen is you will have a page with 90% empty space and maybe 1 or 2 active rows, and then another page like 80% empty space, right? So if I do a full table scan, like a normal full table scan, it becomes really slow. Why? Because all the rows that I actually need are in the tail end, and I'm doing I/O right in the beginning just to fetch a page with a bunch of empty space, which is really sad. It just makes me really sad to fetch a page. You do all the work. It's just, you look at it, it's like, oh, it's all empty space. My God, why is this all empty? So this is kind of the sad part of bloat, you know, as you pitch. In indexes is like it's its own beast actually, right? Because you also have the same effect on indexes. Indexes, you can argue that indexes might be a little bit worse because as you delete stuff from the table space, the empty spaces can be reused by inserting new rows because we don't have orders in the heap, right? It doesn't have to be ordered per se. But in the index, it has to be ordered. So it's highly unlikely that if you delete something in the index and there is like a little bit of a gap, highly unlikely that there will be another key that will go exactly in the place that you just deleted. Very highly unlikely. So the gaps and the fragments and the bloat in the index is actually worse than the table, right? And that's why you need to rebuild the indexes, right? And you can use rebuild index concurrently to avoid locking the entire table. I mean, I did a site like called pglocks.org that tells you, okay, this function will block these guys, and if you do this, then it will block these guys. It's a very cool way, because I got tired looking at the matrix and the doc and like, oh yeah, I need to build something that makes things a little bit easier. Yeah, so that's what I wanted to talk about. It's a pretty cool concept, and I can really talk more about that. And then shout out to Nikolai. I'm trying to remember his name. Nikolai from Twitter. He's been on this grind on marathon, writing all this stuff, and I absolutely enjoy his content. So shout out to him. Right, he gave me the idea for this video to just talk about that, details. But yeah, see you in the next one.